Power over Ethernet.
Power over Ethernet or PoE describes any of several standardized or ad hoc systems which pass electrical power along with data on Ethernet cabling. This allows a single cable to provide both data connection and electrical power to devices such as wireless access points or IP cameras. Unlike standards such as Universal Serial Bus which also power devices over the data cables, PoE allows long cable lengths. Power may be carried on the same conductors as the data, or it may be carried on dedicated conductors in the same cable. There are several common techniques for transmitting power over Ethernet cabling. Two of them have been standardized by IEEE 802.3. Since only 2 of the 4 pairs are needed for 10-T or 100-TX, power may be transmitted on the unused conductors of a cable. In the IEEE standards, this is referred to as alternative B. Power may also be transmitted on the data conductors by applying a common mode voltage to each pair. Because Ethernet uses differential signaling, this does not interfere with data transmission. The common mode voltage is easily extracted using the center tap of the standard Ethernet pulse transformer. This is similar to the phantom power technique commonly used for powering audio microphones. In the IEEE standards, this is referred to as alternative A. In addition to standardizing existing practice for spare pair and common mode data pair power transmission, the IEEE PoE standards provide for signaling between the power source equipment, PSE, and powered device, PD. This signaling allows the presence of a conformant device to be detected by the power source, and allows the device and source to negotiate the amount of power required or available. Up to a theoretical 51 watts is available for a device, depending on the version of the standard in use and the vendor of the hardware.
Standard development.
The IEEE standard for PoE requires Category 5 cable or higher for high power levels, but can operate with Category 3 cable if less power is required. Power is supplied in common mode over 2 or more of the differential pairs of wires found in the Ethernet cables and comes from a power supply within a PoE-enabled networking device such as an Ethernet switch, or can be injected into a cable run with a mid-span power supply. The original IEEE 802.3 AF 2003 PoE standard provides up to 15.4 W of DC power, minimum 44 VDC and 350 mA, to each device. Only 12.95 W is assured to be available at the powered device as some power is dissipated in the cable. The updated IEEE 802.3 A 2009 PoE standard, also known as PoE Plus or PoE Plus, provides up to 25.5 W of power. The 2009 standard prohibits a powered device from using all 4 pairs for power. Some vendors have announced products that claim to be compatible with the 802.3 AT standard and offer up to 51 W of power over a single cable by utilizing all 4 pairs in the Category 5 cable. Both of these amendments have since been incorporated into the IEEE 802.3-2012 publication.
Comparison with other integrated data and power standards.
PoE provides both data and power connections in one cable, so equipment doesn't require a separate cable for each need. For equipment that does not already have a power or data connection, PoE can be attractive when the power demand is modest. For example, PoE is useful for IP telephones, wireless access points, cameras with pan tilt and zoom, PTZ, and remote Ethernet switches. PoE can provide long cable runs, for example 100 meters, 330 feet, and deliver 12 W of galvanically isolated power. PoE Plus provides even more power. There are competing data and power technologies. The Universal Serial Bus, USB, provides both data and power, but it is designed for short cables with a maximum length of 5 meters, 16 feet, and provides less than 2.5 W of non-isolated power. It is less expensive than PoE, and works well for low-power peripherals such as a computer mouse, a headset microphone or a serial port. Some peripherals, such as speakers, scanners and printers, need more power than USB can provide. IEEE 1394, FireWire, is similar to USB but can provide substantially more power, 45 W, at a distance of 4.5 m. If a device already has power available but no data link, then PoE may not be attractive. A wireless data connection such as IEEE 800 2.11 may be more economical than running a data cable for the device. Alternatively, there are power line communication technologies that can use power cables for transmitting data. Using some power line modems may be more economical than running a cable. When data rate and power requirements are both low, other approaches may be viable. Mobile phones, for example, use batteries for power and antennas for communication. Remote weather sensors use very low data rates, so batteries, sometimes supplemented with solar power, and custom wireless data links are used. Depending on the application, some of the advantages with PoE over other technologies may be: inexpensive cabling carries both data and power, power to equipment can be remotely cycled, fast data rate.
Uses.
Some types of devices powered by PoE include VoIP phones, IP cameras, network webcams, wireless access points, IPTV decoders, network routers, a mini network switch installed in distant rooms, to support a small cluster of ports from one uplink cable. Mini switches do not usually provide PoE on their output ports. Many modern VoIP phones include a 2-port mini switch that can provide a network connection for a nearby computer, network intercom/paging/public address systems and hallway speaker amplifiers, wall clocks in rooms and hallways, with time set using network time protocol, outdoor roof-mounted radios with integrated antennas, 802.11 or 802.16-based wireless CPEs, customer premises equipment, used by wireless ISPs, industrial devices, sensors, controllers, meters etc., access control and help points, intercoms, entry cards, keyless entry, etc., lighting controllers, remote point of sale, POS, kiosks, physical security devices and controllers.
Terminology. Power sourcing equipment.
Power sourcing equipment, PSE, is a device such as a switch that provides, sources power on the Ethernet cable. The maximum allowed continuous output power per cable in IEEE 800 2.3 is 15.40 W. A later specification, IEEE 800 2.3 AT, offers 25.50 W. When the device is a switch, it is commonly called an EIN-span, although IEEE 800 2.3 refers to it as endpoint. Otherwise, if it's an intermediary device between a non-PoE capable switch and a PoE device, it's called a mid-span. An external PoE injector is a mid-span device.
Power device.
A powered device, PD, is a device powered by a PSE and thus consumes energy. Examples include wireless access points, IP phones, and IP cameras. Many powered devices have an auxiliary power connector for an optional, external, power supply. Depending on the PD design, some, none, or all power can be supplied from the auxiliary port, with the auxiliary port sometimes acting as backup power in case of PoE-supplied power failure.
Power management features and integration.
Most advocates expect PoE to become a global long-term DC power cabling standard and replace wall-wart converters, which cannot be easily centrally managed, waste energy, are often poorly designed, and are easily vulnerable to damage from surges and brownouts. Critics of this approach argue that DC power is inherently less efficient than AC power due to the lower voltage, and this is made worse by the thin conductors of Ethernet. A typical 48-port Ethernet switch has a 50 W to 80 W power supply allocated for the traditional Ethernet switch and transceiver IC. Over and above this it requires typically a 740 W, for 802.3 AF, to 1480 W, for 802.3 AT, power supply allocated solely for PoE ports, permitting a maximum draw on each. This can be quite inefficient to supply through long cables. However, where this central supply replaces several dedicated AC circuits, transformers and inverters, and prevents expensive human interventions, AC installations, the power loss of long-thin DC cable is easily justifiable. Power can always be introduced on the device end of the Ethernet cable, radically improving efficiency, where AC power is available. Other challenges of PoE include power failure and short-circuiting power data wires from a crushed network cable or mispunched RJ45 wall jack. This could possibly transfer a 44-volt PoE voltage into a 2-volt data wire, inadvertently resulting in equipment failure and data loss. The issue of heat generation typically generated remotely at the end devices is now transferred into the data room switch with increased heat dissipation within the data center room, altering the British thermal unit cooling requirement specifications as well as the power consumption.
Switch power features.
The switches themselves often contain active, smart, or managed power management features to reduce AC draw of all devices involved. Multi-protocol teaming standards, GEN 9960, GHN, and IEEE 1905, and handoff standards, IEEE 800 2.21 generally rely on simulating Ethernet features in other media. By late 2011, some of the energy management features are proprietary. Advertising for Power over Ethernet devices usually cites its green features, including less packaging and improvements over previous models.
Integrating EE and PoE.
After integration with the IEEE 800 2.3R's Energy Efficient Ethernet (EEE) standard, the energy management capabilities of the combined standard are expected to be good. Pre-standard integrations of EE and PoE, such as Marvell's ePoE outlined in a May 2011 white paper, claim to achieve a savings upwards of 3 watts per link, extremely significant across the tens of millions of new links shipped each year. These losses are especially significant as higher power devices come online. Marvell claims that
Standard implementation.
Standards-based Power over Ethernet is implemented following the specifications in IEEE 800 2.3 AF 2003, which was later incorporated as Clause 33 into IEEE 800 2.3-2005, or the 2009 update, IEEE 800 2.3 AT. A phantom power technique is used to allow the powered pairs to also carry data. This permits its use not only with 10 base T and 100 base TX, which use only 2 of the 4 pairs in the cable, but also with 1000 base T, gigabit Ethernet, which uses all 4 pairs for data transmission. This is possible because all versions of Ethernet over twisted pair cables specify differential data transmission over each pair with transformer coupling. The DC supply and load connections can be made to the transformer center taps at each end. Each pair thus operates in common mode as one side of the DC supply, so 2 pairs are required to complete the circuit. The polarity of the DC supply may be inverted by crossover cables. The powered device must operate with either pair, spare pairs 4 to 5 and 7 to 8, or data pairs 1 to 2 and 3 to 6. Polarity is required on data pairs, and ambiguously implemented for spare pairs, with the use of a diode bridge. Notes: most switched power supplies within the powered device will lose another 10 to 25% of the available power. More stringent cable specification allows assumption of more current carrying capacity and lower resistance, 20.0 ohms for Category 3 versus 12.5 ohms for Category 5.
Powering devices.
2 modes, A and B, are available. Mode A delivers power on the data pairs of 100 base TX or 10 base T. Mode B delivers power on the spare pairs. PoE can also be used on 1000 base T Ethernet, in which case there are no spare pairs and all power is delivered using the phantom technique. Mode A has 2 alternate configurations, MDI and MDIX, using the same pairs but with different polarities. In Mode A, pins 1 and 2, pair number 2 in T568B wiring, form one side of the 48 VDC, and pins 3 and 6, pair number 3 in T568B, form the other side. These are the same two pairs used for data transmission in 10-base-T and 100-base-TX, allowing the provision of both power and data over only two pairs in such networks. The free polarity allows PoE to accommodate for crossover cables, patch cables and auto MDIX. In Mode B, pins 4 to 5, pair number 1 in both T568A and T568B, form one side of the DC supply, and pin 7 to 8, pair number 4 in both T568A and T568B, provide the return. These are the spare pairs in 10-base-T and 100-base-TX. Mode B, therefore, requires a 4-pair cable. The PSE, power sourcing equipment, not the PD, powered device, decides whether power mode A or B shall be used. PDs that implement only mode A or mode B are disallowed by the standard. The PSE can implement mode A or B or both. A PD indicates that it is standards compliant by placing a 25K resistor between the powered pairs. If the PSE detects a resistance that is too high or too low, including a short circuit, no power is applied. This protects devices that do not support PoE. An optional power class feature allows the PD to indicate its power requirements by changing the sense resistance at higher voltages. To stay powered, the PD must continuously use 5 to 10 mA for at least 60 milliseconds with no more than 400 milliseconds since last use, or else it will be unpowered by the PSE. There are two types of PSEs, EN spans and mid spans. EN spans, commonly called PoE switches, are Ethernet switches that include the power over Ethernet transmission circuitry. Mid-spans are power injectors that stand between a regular Ethernet switch and the powered device, injecting power without affecting the data. EN spans are normally used on new installations or when the switch has to be replaced for other reasons, such as moving from 10/100 Mbps to 1 Gbps or adding security protocols, which makes it convenient to add the PoE capability. Mid-spans are used when there is no desire to replace and configure a new Ethernet switch, and only PoE needs to be added to the network. IEEE 800 2.3 capable devices are also referred to as Type 2. An 800 2.3 PSE may also use Layer 2 communication to signal 800 2.3 capability. Class 4 can only be used by IEEE 800 2.3 Type 2 devices, requiring valid Class 2 and Mark II currents for the power-up stages. An 800 2.3 device presenting a Class 4 current is considered non-compliant and, instead, will be treated as a Class 0 device.
Configuration via Ethernet Layer 2 LLDP.
The setup phases are as follows. PSE, provider, tests PD, consumer, physically using 800 2.3 phase Class 3. PSE powers up PD, PSE powers up PD, PD sends to PSE, I'm a PD, max power equals X, max power requested equals X, PSE sends to PD, I'm a PSE, max power allowed equals X. PD may now use the amount of power as specified by the PSE. PD may now use the amount of power as specified by the PSE. The rules for this power negotiation are: PD shall never request more power than physical 800 2.3 class, PD shall never draw more than max power advertised by PSE, PSE may deny any PD drawing more power than max allowed by PSE, PSE shall not reduce power allocated to PD, that is in use, PSE may request reduced power, via conservation mode. 10.
Non-standard implementations. Cisco.
Cisco manufactured WLAN access points and IP phones many years before there was an IEEE standard for delivering PoE. Cisco's original PoE implementation is not software upgradable to the IEEE 800 2.3 standard. Cisco's original PoE equipment was capable of delivering up to 10 W per port. The amount of power to be delivered is negotiated between the endpoint and the Cisco switch based on a power value that was added to the Cisco proprietary Cisco Discovery Protocol, CDP. CDP is also responsible for dynamically communicating the voice VLAN value from the Cisco switch to the Cisco IP phone. Under Cisco's pre-standard scheme, the PSE switch will send a fast link pulse, FLP, on the transmit pair. The PD device connects the transmit line to the receive line via a low-pass filter, and thus the PSE gets the FLP in return. And a common mode current between pair 1 and 2 will be provided, resulting in 48 VDC and 6.3 W default of allocated power. The PD has then to provide Ethernet link within 5 seconds to the auto-negotiation mode switch port. A later CDP message with a type length value tells the PSE its final power requirement. A discontinued link pulses shuts down power.
PowerZine.
PowerZine, now a Microsemi brand, have been selling mid-span power injectors since 1999 with its proprietary power over LAN solution. Several companies such as Polycom, 3Com, Lucent and Nortel utilize PowerZine's power over LAN.
Passive.
Most passive applications use the pin-out of 802.3 ARF mode B, with DC plus on pins 4 and 5 and DC minus on 7 and 8, see chart below. Data is then on 1 to 2 and 3 to 6. This limits operation to 100 Mbps. Gigabit passive injectors use a transformer on the data pins to allow power and data to share the cable and is typically compatible with 802.3 ARF mode A. In the common passive PO system, the injector does not communicate with the powered device to negotiate its wattage requirements, but merely supplies power at all times. Passive mid-span injectors up to 12 ports simplify installations. Devices needing 5 volts cannot use PO at 5V on Ethernet cable beyond about 15 feet, 4.6 m, due to IR loss, so a 24V or 48V to 5V DC-DC converter is required at the remote end. Passive DC to DC injectors also exist which convert a 9V to 36V DC input power source to a stabilized 24V1A or 48V 0.5A PO feed with plus on pins 4 and 5 and on pins 7 and 8. These DC to DC PO injectors are used in various telecom applications.
Power capacity limits.
Category 5 cable uses 24 Fluorines conductors, which can safely carry 360 mA at 50V according to the latest TIA ruling. The cable has 8 conductors, only half of which are used for power, and therefore the absolute maximum power transmitted using direct current is 50V x 0.360 AX2 equals 36 W. Considering the voltage drop after 100 m. A PD would be able to receive 31.6 W. The additional heat generated in the wires by PO at this current level, 4.4 watts per 100 meter cable, limits the total number of cables in a bundle to be 100 cables at 45 DEGC, according to the TIA. This can be somewhat alleviated by the use of Category 6 cable which uses 23 Fluorines conductors.